Hello, and welcome to our stoichiometry video activity. So we're going to be practicing a skill called stoichiometry today, and that basically involves converting between amounts of two different chemicals. And Morpheus here has got an important hint for us that we can't do stoichiometry without converting to moles. So stoichiometry is always going to involve some sort of mole-to-mole ratio for two different compounds. And in order to figure out this ratio, we need a balanced chemical equation. So where does this 4 come from in our ratio? It comes right from our balanced equation. It's the coefficient. And this 3 right here, again, comes from our balanced equation. So in order to do this, we need to be able to balance equations. If you don't know how to do that, see the videos, the previous videos, or the third-party videos. There are some helpful ones down there. So our question asks, how many moles of iron are needed to react with 12 moles of oxygen? So this is a pretty typical stoichiometry problem. We're converting between amounts of two different chemicals, in this case oxygen and iron. So here's our 12 moles of oxygen. Then we take our ratio from balanced equation. Moles of oxygen go on the bottom, so those will cancel. And we do our good old-fashioned unit cancellation, which hopefully you guys are getting pretty handy at this point. And we end up with 16.0 moles of iron. So this is actually a really powerful technique. You might be wondering, well, why the heck would I care about this? It's useful all over the place. If you're building an engine, you need to figure out how much fuel and how much air need to go together. If you're administering a drug to a patient, like an antidote for a toxin, you need to be able to figure out what ratio of antidote you need for the amount of toxin in their bloodstream and stuff. So just a really, really useful method right here. So moving on from there, we have another example. How many moles of CO2 can be produced when 2.25 moles of propane react according to our balanced equation right here? So I want to point out on a quiz or exam, I'm probably not going to be this nice. I'm probably going to give you unbalanced equations. So on quizzes or exams, make sure you double check that the equations are balanced. And so now to solve our problem right here, we're given our 2.25 moles of propane, and we are going to take from our balanced equation right now. And so for every 3 moles of CO2, we get that again from our balanced equation, that's going to correspond to 1 mole of our propane. And the moles of propane go on the bottom so we can get our unit cancellation to work out. And we crunch our numbers and we end up with 6.75 moles of CO2 being formed in this reaction. So I'd like you to now pause the video and please complete question number 1. Alright, welcome back. We are now going to step up the awesome a little bit. We're going to do stoichiometry, but now we're going to start with mass and we're going to convert it to mass. So we're going to do grams to grams or mass to mass stoichiometry. So this is going to involve more steps, and we're going to need to use the molar mass material we learned in the previous video activity. So our question is, how many grams of CO2 can be produced when 54.6 grams of, that is acetylene right there, are burned? And so we have a balanced equation right here, and again on a quiz or exam, I'm probably going to be mean and give you unbalanced equations, so make sure you double check that. But we're going to take our 54.6 grams of acetylene, and we're going to use our molar mass in order to convert that into moles. So where does our molar mass come from? Well, that's from our periodic table. We talked about that before. So this is going to be the mass of 2 carbons plus 2 hydrogens. So there is our molar mass. That's going to convert us into moles. And a trusty meme on a previous part taught us that we need to do a moles to moles comparison to solve any stoichiometry problem. So here's our moles to moles comparison. 4 moles of CO2 for every 2 moles of acetylene. And we set that up, bam, and those cancel out. And then finally we're asked for grams of CO2, so we're going to use our molar mass of CO2, which we again get from the periodic table. It's the mass of a carbon and 2 oxygens. So it's about 44.0 grams of CO2 in every mole. So that cancels that right there. We crunch all our numbers and we end up with 185 grams of CO2 being formed by this reaction. So it's like before, but we have to use the molar mass to convert into moles, so we can do our moles to moles comparison, and then we have to do our molar mass, a different molar mass, to get out of moles back into grams. And so another example is on this slide. Determine the mass of NH3 that can form when 62.3 grams of N2 react. So once again, we need our equation right here. Boom, there's our equation, our balanced equation. Our 62.3 is given in our problem. Then we're going to use our molar mass here. So notice because we have N2 right here, it's going to be 2 times our 14.01 that's on our periodic tables. So remember, if you have 2 of something, you need to double that mass. And then right here from our balanced equation, that's where we get these values from. And then finally our molar mass over here. This is now our molar mass for ammonia. So that's the mass of nitrogen plus the mass of 3 hydrogens. So we check our unit cancellation. Bam, bam, bam. The unit cancellation looks good. And if we crunch all our numbers, we're going to end up with 75.7 grams of ammonia. So I want to emphasize here, you're going to want to do a lot of practice problems. Make sure that you do a bunch of practice problems, because otherwise you're not going to lock down this skill. So practice, practice, practice. All right, so speaking of which, why don't you pause the video and please complete question number 2. All right, welcome back everybody. We are now going to take a look at applied stoichiometry skill. We're going to be talking about percent yield. So in order to describe our percent yield, we need to first define some other terms. We have our theoretical yield, and so this is the maximum amount possible if our process is 100% efficient. So if our reaction is perfect, and this rarely happens in the real world, we'll end up with our theoretical yield. But more often than not, we have an actual yield that's going to be less. And this is going to be our amount of product that we actually obtain. So again, the actual yield is what happens in the real world. The theoretical yield is what happens if things work 100% perfectly. And so our percent yield is going to equal our actual yield divided by our theoretical yield times 100. And this is generally going to be some number less than 100. So it could be anywhere from the 90s to the teens, anywhere in that range. You know, we could have a wide array of percent yields. So how do we solve this? Actual yield's usually given in the problem, but we usually have to solve for our theoretical yield. How do we do that? Well, thankfully we have example problems. What is the percent yield of the reaction if 50.0 grams of lithium hydroxide give 72.8 grams of lithium bicarbonate? And so here's our balanced chemical equation. And now to plug and chug. So here's our amount of lithium hydroxide that's given in the problem. So there's our amount of starting material. Then we're going to use our molar mass to convert that to moles, and then our molar ratio from our balanced equation. Then our molar mass for our lithium hydroxide. So just like we did in the previous 2 examples, just a regular old stoichiometry problem. And we end up with, once we're all done, 142 grams of lithium bicarbonate. So what have we calculated here? This is our theoretical yield right here. So this is how much we'd get if our reaction was 100% perfect. But if we look, we see that we only make about half of that much. There's our actual yield right there. So let's go ahead and calculate our percent yield. So we're going to take our actual yield, our 72.8 grams that was given in the problem, and divide it by the theoretical yield we calculated on the previous page, and then multiply that amount times 100. And so like I said, we end up with roughly a 50% yield. So, you know, our reaction is only about 50% efficient. Only about half of our reactant was converted to the product we were looking for. So I'd like you to now pause the video and please complete questions 3 and 4 on the activity. All right, folks, welcome back. We have just one more topic left, and that has to do with heat absorbed or released by reactions. So we have 2 major classes of reactions. We have exothermic reactions, and so exothermic reactions are reactants have potential energy stored in them and our products are lower in potential energy. So where does the extra potential energy go? It's heat that's going to be released in the reaction. So again, if our reactants have more potential energy than our products, our reaction is going to release heat. We call this an exothermic reaction. And what's going to happen here is our reaction is essentially going to get hot. We're going to see an increase in temperature. So right here, if we take carbon and we burn it with oxygen, we're going to make CO2, but also a bunch of heat. And this is a reaction you're familiar with. When you burn charcoal on your grill, it releases a lot of heat, and that's how you cook your meat. So notice here the negative sign. People often use the negative sign to indicate that heat is released. So that means heat is leaving our reaction and going out into the world. And how do we observe this? Well, what we're going to see is these exothermic reactions are actually going to increase in temperature. They're going to get hot. And so think about like when you burn something or when you exercise intensely and your body temperature goes up. Those are examples of exothermic reactions. Heat's being released by those reactions. Now, an endothermic reaction, our reactants are lower in potential energy than our products. And so where does that energy come from that we're storing? It's going to come from the environment. So our heat is going to enter the reaction. So endothermic reactions, endo means inside. That means the heat's going to enter our reaction. And what we're going to see is that the temperature is actually going to go down on an endothermic reaction. These endothermic reactions, we're actually going to see a temperature decrease rather than temperature increase. And notice that our sign here for our heat is positive, meaning heat's being absorbed or entering. And on the previous reaction, heat was listed as a product, but now you'll see that heat's listed as a reactant. So key differences here. Exothermic reactions release heat. Products are lower in energy than reactants. Temperature goes up. Endothermic reactions the opposite. Temperature goes down. Heat's a reactant. And our products are higher potential energy than our reactants. So let's take a look at an example problem here. We're actually able to do stoichiometry type problems with this sort of thing. And so if we have 15.0 grams of NO, how many kilojoules of heat were released? So here's our balanced equation, or excuse me, how many kilojoules of heat were absorbed. So here's our balanced equation. Here is our heat of reaction. So we're going to take this number down here. We're going to use a conversion factor to convert this into moles. So it's going to be 30 grams of NO. So that's just taken from our periodic table. There's our molar mass. And from our balanced equation, for every 2 moles of NO, that's going to correspond to our 180 kilojoules. And so if we do all our fancy schmancy unit cancellation here, we end up with 45.0 kilojoules of heat being absorbed by this reaction. So again, the key thing here is like a regular stoichiometry problem, except that rather than doing a moles to moles comparison like we do normally, we do a moles to energy comparison. And one last example problem here. How many grams of O2 reacted if 306 kilojoules were released from the following reaction? So now we'll be going in the reverse direction. So we're told 306 kilojoules, so we're going to start with that number. And then we look at our balanced chemical equation here, and for every 2 moles of O2, that's going to correspond to 213 kilojoules of heat. So the kilojoules of heat go on the bottom in this case to get our unit cancellation to work out. Here's our 2 moles from our balanced equation right here. And then our molar mass right here, because it asks for grams of O2. And so we end up with 91.9 grams of O2. So there's one in the reverse direction. So congratulations, you made it through. Please complete questions 5 and 6 on the activity.